Hi, this lesson is about approximating the area under a curve. We're going to use rectangles in order to approximate it. But before we do that, we need to review summation notation. So this is the symbol for summation. It looks like this. It's a Greek letter called sigma, and it stands for the sum of a bunch of terms. So the terms that you're adding is this one that we're calling a sub I, and that defines the formula for whatever the ith term is. The values at the bottom and at the top of the summation symbol tells you where your terms begin and end. So I, called the index, is like a counter. So we often start at 1, but it doesn't have to. So we start wherever I is equal to that number, and we end at some value n, and so that will be the nth term. I and n are common variables used to define these, but there's others. Sometimes j and k are often used as well. So in general, when you're taking the sum of some numbers, and so here if my index is from j equal to m to n, then a sub j is a sub m plus a sub m plus 1 plus a sub m plus 2. So these index values keep increasing by 1 until you get to the last one. And again, the last one is indicated by what's at the top of the summation symbol. Okay. So linearity of summation notation. So these are just some properties that we should know. So if you're taking the summation of two terms, a sub j plus or minus b sub j, so adding or subtracting, that's the same as taking the individual sums and then adding and subtracting them. So you get the same result either way. The second one says that if you have the sum as j goes from n to n of c a sub j, well, c is a constant, and you can think of it as a number that you can factor out. So that's the same as multiplying c by the sum instead of multiplying each term by c. And the last one is that if you have a sum as j goes from 1 to n, so here, in order for this to make sense, it has to start at 1. The beginning value has to start at 1. K is a constant. So if you're adding k n times from 1 to n, that's the same as n times k. So repeated addition is just multiplication. So if I said the sum as j goes from 1 to 3 of 2, that is 2 plus 2 plus 2. You do it 3 times, but that's the same as 3 times 2. You get the same result, and that's exactly what this is telling you. All right, so let's practice using some of these summation notation properties or notation that we've just talked about. So we want to take the sum as j goes from 1 to 4 of j cubed plus j plus 7. All right, well, I'm going to handle each term separately. So I'm going to take the sum of j cubed, the sum of j, and then the sum of my constant 7. All right, so j cubed tells you that for the first summation, every value of j from 1 to 4 has to get raised to the third power. So that's what you see on this line. That'll be 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed. Then we have to handle the second sum. Well, here it's just j, so that's just 1 plus 2 plus 3 plus 4. And then the last one, that's using the last linearity property that I talked about, is that you have the sum of a constant, and that's repeated 4 times, so it's the same as 4 times 7. So when you combine the terms inside of the parentheses in the last one, you'll get 100 plus 10 plus 28, which means that the entire summation is equal to 138. All right, so let's do another example. Suppose that the sum as I goes from 1 to 12 of a sub I is equal to 24, and a sub 1 is equal to negative 2. And we're being asked to find the sum as I goes from 2 to 12 of a sub I. Well, we know that the sum as I goes from 1 to 12, that means that you're adding these a terms 12 times. So I have a sub 1 plus a sub 2 plus a sub 3, all the way up to a sub 12. Okay, but if I take a sub 1 away from this summation, then you have a sub 2 plus a sub 3 plus a sub, etc., all the way up to a sub 12. So then instead of starting with the first term, you start with the second term, a sub 2. But when you start with the second and end with the 12th, well, that is actually the summation that we were asked to find. So now we just have to plug in the numbers that we know. The sum as I goes from 2 to 12 is equal to the sum as I goes from 1 to 12 of a sub I minus a sub 1. So you're taking away the first term. So it's given in the problem that the summation from 1 to 12 is 24. That's right here in the original problem. And a sub 1 is negative 2. That's right here. When you plug in the numbers, you get that the sum as I goes from 2 to 12 has a value of 26. All right, so here's another. We want to expand the sum as j goes from 3 to 7 of k over j plus 1. Well, notice that I have two variables in my term here, k over j plus 1, but my index starts from j equal to 3 to 7. So when you substitute in from 3 to 7, you're only plugging into j, not to k. K stays as a constant. So when you expand it, you get this line right here. I have k over 3 plus 1 plus k over 4 plus 1 plus k over 5 plus 1 and k over 6 plus 1. So when you simplify that line, you get k over 4 plus k over 5 plus k over 6 plus k over 7. So since k is a common factor among these four terms, I factor it out here. And so I'm left with 1/4, k times 1/4 plus 1/5 plus 1/6 plus 1/7. So the LCD of 4, 5, 6, and 7 is 420. So in order to combine those fractions, you need a common denominator of 420. So the first term gets multiplied by 105, the second one by 84, the third one by 70, and the last one by 60, so that the common denominator is 420. When you combine the numerators, you get k, 319 over 420. That does not simplify, which is the same as 319 over 420k. Okay, so let's turn our attention to areas. We want an area under a curve called f of x defined on a closed interval from a to b, and we're going to estimate the value of this area by using rectangles. Okay, so unlike geometric shapes like squares and circles and rectangles, triangles, where we have an actual formula, when you have a curve like this, f of x, well, we don't have a formula. So we actually are going to estimate what that area is by using rectangles. So if you can imagine taking this space from A to B and breaking it up into equal subintervals, let's say, I'll do a few right here. So I have 1, 2, 3, 4, 5, 6, 7, 8 subintervals. And each of those subintervals have a corresponding x value. Let's call this x sub 1, x sub 2, x sub 3, 4, 5, 6, 3, 4, 5, 6, and this x sub 7, and then my eighth one is at b. And a would be x sub 0, and this would be x sub 8, okay? So each of those subintervals have a corresponding function value. So this one here would be f of x sub 1. And for example, this one here would be f of x sub 7, and you get the idea in between. So if you were to actually extend out each of these, you can see that I create a rectangle when I get the function value and extend it across to the previous rectangle. And so I get a bunch of little subrectangles in between the interval from A to B. Now, in some cases, your area will be overly counted, like you see right here. That's too much space because you're only interested in the part that's shaded. And in some cases, you'll be undercounting the area, like right in here, where you're not accounting for some of the space underneath the curve. Okay, but we know how to calculate the area of a rectangle because the area of a rectangle is just length times width. Length times width. So the length would be your function value at whatever your ith interval is. And your width would be the difference from the previous one to the from the next one to the previous one. So this would be what we would consider to be the length of the rectangle. And this one here would be the width. All right, so let's clean this up a little bit. So let's actually use this. So let me give you a couple of formulas just so that this makes more sense. We're going to, and notation, we're going to let n be the number of rectangles used to compute the area, because you do have to make a decision as to how many you use. I just arbitrarily picked 8 in that picture above, but it could be anything you want. Your delta x will represent your width, the difference between two consecutive x values. And we compute that by taking your interval, because the function will be defined on an interval from A to B, and dividing by n, the number of rectangles. And we want that width of the rectangles to be consistent throughout. We're going to let I be the ith rectangle, where I starts at 1 all the way up to n. So if you have n equal to 10, then you'll have 10 rectangles. And f of x sub I will be the length or the height of the ith rectangle. And so the area, the total area under the curve, will be the sum of all of the individual computations for area of the rectangle. So it'll be length times width added up for however many rectangles you have. And because my width will be consistent, you could always factor that out of the summation and just sum up all of the heights or lengths of the rectangle from the first one to the last one. So that's basically what we're going to be doing in these next couple of examples. So we want to estimate the area under the curve of f of x equal to x squared on the interval from 0 to 1 by using 4 rectangles. So whenever you're asked to estimate or find the area under a curve, you're basically trying to find the area between the curve and the x-axis. It could be above the x-axis or below the x-axis, but it's basically your x-axis will be one of the boundaries unless you are told otherwise. So for now, the x-axis is one of the boundaries of our area. So first I'm going to compute my delta x. And so remember, I told you above, that delta x is the formula b minus a divided by n. So my a and b is 0 and 1 in this problem, and my n is 4. So delta x is 1/4. 1 minus 0 divided by 4. So that means that is the width of each rectangle that we're going to use in order to estimate the area underneath this curve. Okay, so if you look at the area, this is a sketch of what you see. From 0 to 1, we know that this is a parabola, but we're not going to show the whole parabola, just the part from 0 to 1. So I want to show every quarter, right, because of our computation here. I want to show every quarter from 0 to 1. So that means when you start at 0, the next quarter is a quarter, the next quarter is a half, the next quarter is 3/4, and the last one is at 1. So if you look at this picture, you can extend the heights of each of these in order to create a rectangle. Okay, but there's two different perspectives that you can take here. You can look at the left-hand endpoint or at the right-hand endpoint of every rectangle. So here I have a rectangle 1. Let me put this a little higher. Here I have rectangle 1, rectangle 2, rectangle 3, and rectangle 4. And rectangle 1, 2, 3, and 4 have a corresponding height to them that changes as you progress throughout. Okay, so if I start from the left-hand endpoint, I'm just going to change my color here for a second. So if I look at the left-hand endpoint of my first rectangle, the left-hand endpoint of this rectangle is at the origin. And if that determines the height, well, there isn't a rectangle at all here. But let's continue with left-hand. If I go to the next one and determine that this is the height of the rectangle, and I go across, then the area defined by that is this one here. So I'm definitely undercounting when I'm on the left. If I go to the next left-hand endpoint of rectangle 3, this is the area of the rectangle. So again, I have, I'm undercounting, so all of this white space in here, just above that, what I just shaded in, is not being counted. And then my last left-hand endpoint of the fourth rectangle, well, that means I extend this height across and I get this. All right, so let's compute the sum of those 4 blue rectangles. So remember, it's the length times the width. I happen to have written the width first, because remember, it's a quarter. We calculated that with delta x. So it's 1/4 times the height of the first rectangle, well, that's 0. Then it's 1/4 times the height of the second rectangle, well, that's 1/16. And how did I figure that out? Well, I computed all of the heights here in this table. When I go to the third one, the third rectangle, 1/4 is the width. The height is also a quarter. And the last one is a quarter times 9/16. You should have 4 summations here because I'm using 4 rectangles. And this notation means left endpoints, 4 rectangles. So L for left, and the 4 of subscript, the 4 in the subscript means 4 rectangles. I'm going to factor out the 1/4 because that was consistent throughout. So I have 1/4 times, and then what's inside of the parentheses are all of the heights. So that's 0 plus 1/16 plus 1/4 plus 9/16. In the next line, I got a common denominator of 16. So I have 1/4 times 1/16 plus 4/16 plus 9/16. And that leaves you with 1/4 times 14/16. When you simplify, you get 7/32. And if you compare it to what the decimal answer would be, you get 0.21875. So that's an approximation of the area, but as I showed you above, it's an under approximation because all of those white spaces between the blue rectangle and the orange curve of y equals x squared is not being counted in this calculation right here. Okay, so now let's look at it from the perspective of right-hand endpoints. So that's here in green. And again, in order to illustrate that, I'm just going to change the color of my pen to green. All right, when you're using right-hand endpoints, that means that you're looking at the right side of rectangle 1 and using that height in order to determine the height of the rectangle. Then the area that you are computing is this one that I just colored in green. So you can see from that first rectangle that I am overestimating my area because I have gone beyond the orange curve of x squared. I do the same thing for rectangle 2. Go across the right-hand endpoint, and that is your height of rectangle 2. And so again, it looks like I am overcounting the area. Do the same thing for rectangle 3 and compute that. So again, you have everything that you need under the curve, but then a little more. And then if you go to the fourth rectangle and use the right-hand endpoint as its height, it's again overcounting. So the calculation is right here. R sub 4, R standing for right, 4 standing for 4 rectangles. I have the width times the height for every one of those green rectangles. And so it's 1/4 times a fourth, times 1/16. Then again, the width times the height, 1/4 times a fourth, width times the height, 1/4 times 9/16, and width times the height, that's 1/4 times 1. So those numbers again come from this chart right here. Those are all of the heights. So we started with this one, 1/16, and then we moved down all the way to 1. In the next line, I factored out 1/4, just like I did in the left-hand calculations. And so I have 1/4 times 1/16 plus 1/4 plus 9/16 plus 1. And then I got a common denominator right here. LCD is 16. And when you compute that, you have 1/4 times 30/16. Simplify, and you get 15 over 32, which is 0.46875. This is an overestimate of the actual area. Okay, so now that we understand left and right-hand endpoints, we're going to talk about midpoints. So a midpoint means that I'm going to pick the middle of the rectangle, of each of the 4 rectangles, in order to compute a height based on midpoint. So let me pick a different color. Let's say I pick purple here. So the midpoint of 0 and a fourth here would be 1/8. And the midpoint here would be 3/8. And the midpoint here would be 5/8. And the midpoint here would be 7/8. So you could find those midpoints by averaging the previous number and the sequential number and dividing by 2. So 0 plus a fourth divided by 2 is 1/8. A fourth plus a half divided by 2 is 3/8. Same thing, a half plus 3/4 divided by 2 is 5/8, etc. So you're basically finding the midpoint or the average number between each of the subintervals. Those midpoints also correspond to a height. So that's calculated here in this chart. I have all my x values that I started with. These are my midpoint calculations. So those are the numbers I just mentioned, 1/8, 3/8, 5/8, 7/8. The height is what you see here in the third column. You take 1/8, plug it into x squared, and you get 1 over 64 all the way to 7/8. Square it, you get 49 over 64. All right, so when we calculate m sub 4, it's exactly what you see here. This is the length times the height, the width times the height, the width times the height, etc. Remember, our width is a consistent 1/4 because we're still using 4 rectangles, but our our heights are different because we're at a different value of x. So when you compute all of that, you already naturally have a common denominator of 64. That works out to be 1/4 times 84 over 64. 4 goes into 84 21 times. So your estimation of using midpoints is 21 over 64. So the midpoint calculation is 0.328125. Now, so now you see all three on this same picture. Left-hand endpoint, right-hand endpoint calculation, and midpoint calculation. But the exact area or actual area of the curve is right here. And for now, I'm just going to ask you to take my word for it because we haven't exactly learned how to do that yet. But the actual area under the curve of x squared from 0 to 1 is a third, which we know is 0.333 repeated forever. So the closest estimation is your m sub 4, is using the midpoints. And that will usually be the case. So the left-hand endpoints and right-hand endpoints give you a decent estimation. The midpoint, or m sub 4 in this example, gives you a more precise estimation. All right, so something to keep in mind is right here. This is an important concept. As the number of rectangles n increases, the estimated area computed by the left-hand endpoints, right-hand endpoints, or midpoints gets closer to the exact area, but overall, the midpoint calculations provides a better estimate than the left and right-hand ones. So if in the above example, instead of using 4 rectangles, we used 8 or 12 or 30, our computations would get closer and closer to this value for all of them. L sub 30, for example, R sub 30, and M sub 30 would all get much closer to the value of a third. All right, so let's do another example. We want to estimate the area under 1 plus x squared from -1 to 2 by using 6 rectangles and computing left-hand computations, right-hand computations, as well as midpoint. Right, so the first thing you do is identify that n is equal to 6. That's what was stated in the problem, and compute delta x. Delta x is the difference in your x values. Always start with larger minus smaller. So it's 2 minus -1 divided by the number of rectangles, which is 6. So that works out to be a half. So that means every half unit starting from -1 to 2, I need to figure out what my height is, or my length for the rectangle. So all that work is here. I start with -1 and I keep adding half a unit all throughout the values of x until I get to the end, which is 2. Then I plug it into f of x, which is 1 plus x squared. So when you do that work, you get the values on the right side, which is 2, 5/4, 1, 5/4, 2, 13/4, and 5. So to compute the left-hand endpoints, you might have noticed this in the above example, but when you're computing the left-hand endpoints, you start with the first height and end with the second to last one, because you are not using the very last one, because that would be on the right of the last rectangle. So this is my width right here, and then I add up all of the heights that's in this purple line that I put here on the left. So I have 2, 5/4, 1, 5/4, 2, and 13/4. Skip the 5 at the end. So then we get a common denominator for what's inside the parentheses. Add things up. You have 1/2 times 43 over 4, which is 5.375. Okay, we do the same thing on the right. But on the right, remember your first rectangle, you're not using the very first value because you're looking at the right side of the first rectangle. So you start with the second one and end with the last. So that's what you see here. It's your width of 1/2 times the sum of all of the heights starting with 5/4 and ending at 5. Then you add up what's inside the parentheses, get a common denominator. You end up with 1/2 times 55/4, which is 6.875. Now, if I did the same thing for midpoints, I didn't actually show the calculations here, but you would have to compute the midpoint of each of these pairs, plug in those values. Sorry, I skipped a couple here. You'd have to find the midpoint of each of these pairs, and then compute the height, add those all up, multiply by 1/2, and you get 5.9375. So as I mentioned before, please take my word for it for now, the actual area, or the exact area under the curve is 6. So once again, you see that your midpoint calculation, this was left hand, this was right hand, and the midpoint is here in black. That is the closest one to the actual area. And so in comparison, I didn't calculate this out for you. If I had done the same problem using 3 rectangles instead of 6, my left hand estimate would have been 5, my right hand estimate would have been 8, and my midpoint would have been 5.75. So with only 3 rectangles, which is a very small number of rectangles to estimate area, you can see that the left and right hand endpoint are not close, especially the right hand one. But still, your midpoint is a pretty good estimate with only 3. Okay, so let's move on. So as I mentioned before, as the number of rectangles increases, your estimate gets better and better. And actually, as the number of rectangles approaches infinity, then your estimated area becomes your actual area. They will be the same, equal, no longer an estimate. So an illustration of that would be something like what you see here. So when n is equal to 6 in this first example, you can see that you're missing everything here that I'm coloring in purple. All of that is missing from your computation. But when I double that number, well, I have much less space that is not being computed. So the higher the number of n becomes, the less space you're losing or over counting when you are computing your area. So as n approaches infinity, you're actually filling in the whole curve the way you see here, and you get the entire area. Okay, so let's try to use that concept and learn some new notation. So therefore, when you have an area called f of x on a closed interval from a to b, the area, the actual exact area, is equal to the limit as n approaches infinity of the sum as I goes from 1 to n of f of x sub I star delta x, where, and so let me explain what all this notation means. Delta x is still the width of the rectangle, and it will be the same width all throughout, so it's b minus a over n. F of x sub I star, and this notation varies depending on what book you're using or video that you're watching. So they might use different notation here, but it's basically the height of the ith rectangle. Remember, when you have a curve, although delta x is constant, your height will be changing as the curve goes up and down. And x sub I is going to be your first value plus the delta x sub I. So you have to figure out where your starting value is, and then you add delta x as many times as necessary until you get to the end, which is b. Okay, so when we do numbers, I think that'll make more sense. So, and the limit, well, we're taking the limit because the number of rectangles is approaching infinity. So that limit of that summation is actually called a Riemann sum. It's named after a mathematician. And we'll be talking more about the Riemann sum in this section and the following section. So the Riemann sum is the definition of the area under a curve on a closed interval. And again, it will give you an exact area, not an estimated area, but the theory behind it is based on areas of rectangles and limits. So we're going to use the definition to state the area under the curve of f of x equal to x squared on the interval from 0 to 3. So we're just going to state it based on what the Riemann sum says, but we're not going to actually evaluate it yet. All right, so remember we have to compute delta x. Delta x is b minus a divided by n. So our delta x is 1 over n. Therefore, our area is the limit as n approaches infinity of your function value at I over n times 1 over n. 1 over n is your delta x, and this one here is the height. Now, how do I know that it's I over n? So let's look at this picture. If you start at 0 and you end at 1, then for your intervals, if they are going to have a width of 1 over n, then the first one will be at 1 over n. Then the next one will be 1 over n units more, which is 2 over n. The third one will be 1 over n units more, which is 3 over n. And that process would continue until you get to the end, which is 1, which is n over n. Now, I'm just showing you this to illustrate it, but in theory, these rectangles would be so skinny that you wouldn't be able to distinguish a 1 over n versus 2 over n because they would be very, very close together. So what's the function value at each of these? The function value at 1 over n would be let me fix this, would be f of 1 over n. And here the function value would be f of 2 over n. So when I goes from 1 to n, 1 over n, 2 over n, 3 over n is written as just I over n. And when I is n, well, that's 1, and that's at the end, n over n. Okay, so now we have to plug it into the actual function. Remember, our function is x squared. So that's what you see in the next line. F of I over n is just I over n squared times delta x, which is 1 over n. And in terms of the summation, as I changes from 1 to n, the only thing that changes is the i's. The n doesn't change until we take the limit. So you can actually pull the 1 over n cubed out, and that comes from combining these. So the first one is n squared in the denominator, the second one is n. So that's where 1 over n cubed comes from. And then you're taking the summation as I goes from 1 to n of I squared. Okay, and we'll learn how to evaluate those summations to get the exact area in the next section. All right, so let's repeat the exercise using the definition. Use the definition to state the area under the curve of f of x equal to 9x over x squared plus 6 on the interval from 1 to 3. So again, first we compute delta x. Delta x is 3 minus 1 over n, which is 2 over n. My area is the limit as n approaches infinity of the sum as I goes from 1 to n. So that first part should always look the same. Then we have to plug in our function value. But remember, we're starting at 1, right, because of the interval. And then every 2 over n units, you are moving over to the next rectangle. Okay, but the first rectangle will be 1 plus 2 over n. But the second one will be 1 plus 4 over n, then 1 plus 6 over n. So the way you display that using I, it'll be 1 plus 2i over n. And then the width is right here. Your delta x is 2 over n. So when you plug in those values into the function, remember your function has x's in the numerator and the denominator, you get that your function is 9 times 1 plus 2i over n over 1 plus 2i over n, that sum is squared, plus 6 times your width of 2 over n. So that would be expressing your area in terms of the Riemann sum. Okay, this time we're going in the other direction. You're given a summation, and this is actually your Riemann sum right here. And we want to describe what area that is finding. So we have the limit as n approaches infinity of the sum as I goes from 1 to n of pi over 7n times the tangent of I pi over 7n. Okay, so this is our function, right? This is the function. And this one here is the delta x because it's being multiplied by the function. Let's worry about the delta x first. So delta x equals pi over 7n. And we know that the computation is b minus a over n. So in order for us to get pi over 7n, that means that my b must be pi over 7, my a must be 0, and my denominator is n. So when you simplify this, you get pi over 7n. So therefore, we know that our area is defined on this interval from 0 to pi over 7. And our function is just your tangent. So the limit in the original problem represents the area under y equal to tangent of x on the interval from 0 to pi over 7. Okay, so now you're ready to try the homework for 5.1. Good luck.